Titania is the largest moon of Uranus, a frozen world nearly 1,600 kilometers wide, orbiting far out in the dark regions of the solar system. For a long time, Titania appeared to be just another ancient icy moon, its surface covered with impact craters formed over billions of years, a quiet world that seemed frozen in time. But when scientists examined the moon more closely, they discovered something unexpected. Across Titania's surface stretch enormous canyon systems, gigantic fractures cutting deep through its icy crust. Some of these valleys extend for hundreds of kilometers, forming one of the largest tectonic structures found on any moon. These canyons suggest that Titania was not always a silent, frozen world. At some point in its distant past, powerful forces from inside the moon appear to have pulled its entire crust apart, leaving behind massive chasms that still scar the surface today. What could cause a moon this size to fracture so dramatically? And could these giant canyons reveal something hidden deep beneath Titania's frozen surface? Before we uncover the secrets of this distant moon, consider subscribing to Theories Before Sleep, where we slowly explore the mysteries of the universe. Tonight, we explore Titania, the moon with giant hidden canyons.
Far beyond the warmth of the inner solar system, past the asteroid belt, past the giant rings of Saturn, and even beyond the powerful gravity of Jupiter, lies a region of space where sunlight becomes faint and distant. Out here, the solar system feels quiet. Temperatures fall to hundreds of degrees below freezing, and the sun itself appears as little more than a bright star. In this cold outer region orbits the planet Uranus. Uranus is one of the most unusual planets in the solar system. Unlike the other planets, it rotates almost completely on its side, as if something long ago knocked it over during the early chaos of planetary formation. Because of this strange tilt, its poles experience decades of sunlight, followed by decades of darkness. But Uranus is not alone. Orbiting this distant planet are 27 known moons, each with its own unique characteristics. Some are small, irregular chunks of ice and rock. Others are larger, complex worlds with landscapes shaped by geological processes that scientists are still trying to understand. Among them is the largest moon of Uranus, Titania. At first glance, Titania may not appear remarkable. Compared to the massive moons of Jupiter or Saturn, Titania is modest in size. With a diameter of about 1,578 kilometers, it is smaller than our own moon, and far smaller than giants like Ganymede or Titan, and yet Titania holds secrets that have puzzled scientists for decades. Because when spacecraft finally captured detailed images of its surface, they revealed a world that had clearly been shaped by powerful forces in its distant past. A moon discovered in the age of telescopes. Titania's story begins in the late 18th century, during a time when astronomy was undergoing a revolution. In 1787, the British astronomer William Herschel made an extraordinary discovery. Using a telescope of his own design, Herschel had already identified the planet Uranus only a few years earlier, the first planet ever discovered with a telescope, rather than known since ancient times. But Herschel's observations did not stop there. While studying Uranus more closely, he noticed faint objects moving around the planet. careful observation revealed that these objects were not stars at all. They were moons, 2 of them. One of those moons would later be named Titania. The name itself comes from literature rather than mythology. Unlike most moons in the solar system, which are named after figures from Greek mythology, Uranus's moons follow a different tradition. They are named after characters from the works of William Shakespeare and Alexander Pope. Titania takes its name from the queen of the fairies in Shakespeare's play A Midsummer Night's Dream. It is a poetic name for a world that, even today, remains mysterious. A world that receives almost no sunlight. Titania orbits Uranus at a distance of roughly 436,000 kilometers. At that distance, the Moon completes one orbit around Uranus every 8.7 Earth days. Like many moons in the solar system, Titania is tidally locked to its planet. This means the same side of the Moon always faces Uranus, while the opposite side permanently faces outward into space. But perhaps the most striking feature of Titania's environment is the lack of sunlight. Uranus is located nearly 3 billion kilometers from the Sun. At that distance, sunlight is about 400 times weaker than what we experience on Earth. If you stood on Titania's surface, the Sun would appear tiny in the sky, brighter than a star, but far dimmer than the Sun we know. The temperature here reflects this extreme distance. Surface temperatures on Titania average around -203 degrees Celsius. At these temperatures, water behaves very differently than it does on Earth. Instead of flowing or melting easily, water becomes as hard as rock. Entire mountains and cliffs can be formed from solid ice. In fact, on Titania, much of the landscape is made not of stone, but of frozen water ice mixed with darker, rocky material. This combination gives the Moon its slightly reddish coloration when seen from space. The first close look at Titania. For nearly 2 centuries after its discovery, Titania remained little more than a distant point of light in telescopes. No one knew what its surface looked like. That changed in 1986. That year, the spacecraft Voyager 2 performed a historic flyby of Uranus, the only spacecraft ever to visit the planet. As Voyager 2 approached the Uranian system, its cameras began capturing the first detailed images of the planet's moons. For the first time in human history, Titania transformed from a tiny dot into a real world with landscapes, textures, and geological features. What the spacecraft revealed surprised scientists. Titania's surface was covered in impact craters, as expected for a moon that had existed for billions of years. These craters were created by asteroids and comets that had collided with the Moon throughout the solar system's history. But the craters were not the most interesting discovery. Instead, scientists noticed enormous linear features cutting across the Moon's surface. These features looked like giant fractures, vast cracks that stretched across Titania's icy crust. Some of these structures were hundreds of kilometers long, and they appeared to form deep valleys or canyons, suggesting that parts of Titania's surface had literally been pulled apart. The Great Canyons of Titania. The most dramatic of Titania's geological features is a massive canyon system known as Messina Chasma. This enormous fracture stretches for roughly 1,500 kilometers across the Moon's surface. To understand how large this is, consider this comparison. The famous Grand Canyon on Earth is about 446 kilometers long. Messina Chasma is more than 3 times longer, and that is only one example. Titania's surface contains several other enormous canyon systems, including Messina Chasma, another vast valley carved deep into the moon's crust. These canyons suggest that Titania once experienced intense geological activity, something scientists did not originally expect from a frozen moon so far from the sun. Because normally, worlds this distant tend to be geologically dead. They lack the internal heat required to reshape their surfaces, and yet, Titania's canyons clearly show that, at some point in the past, something powerful was happening beneath its surface, something strong enough to tear the moon's crust apart. A surface frozen in time. Aside from its giant canyon systems, Titania's landscape appears relatively ancient. Large portions of the surface are heavily cratered, suggesting they have not changed significantly for billions of years. Some craters on Titania are over 300 kilometers wide, indicating enormous impacts during the early solar system when collisions were far more common. But interestingly, Titania has fewer craters than some of Uranus's other moons. This detail tells scientists something important. It suggests that Titania's surface may have been partially resurfaced at some point in the past. Geological activity may have erased some older craters, replacing them with newer terrain. In other words, Titania was not always a completely frozen and inactive world. Long ago, it may have been geologically alive. But if Titania once had enough internal energy to reshape its surface, the question becomes obvious. Where did that energy come from? The mystery beneath the ice. To understand Titania's giant canyons, scientists must consider what might be happening inside the moon. Most moons form from mixtures of rock and ice. If a moon is large enough, its interior may contain several layers, a rocky core surrounded by icy materials. In some cases, internal heat can even melt parts of that ice, creating subsurface oceans hidden beneath the surface. We already know that several moons in the solar system contain such oceans. Europa, one of Jupiter's moons, likely hides a vast ocean beneath its icy crust. Saturn's moon Enceladus ejects plumes of water vapor from fractures near its south pole, evidence of liquid water deep below the surface. Even Titan, Saturn's largest moon, may contain an ocean beneath its thick, icy shell. Could something similar exist inside Titania? Some scientists believe it is possible. If Titania once contained a subsurface ocean, the freezing of that ocean over time could have caused the moon's crust to expand and crack. Water expands when it freezes. So if a large ocean inside Titania gradually turned into ice, the expansion might have pushed outward against the crust, creating enormous fractures across the surface. These fractures could be exactly what we see today as Titania's giant canyon systems. But Voyager 2 only photographed about 40% of Titania's surface. The rest of the moon remains largely unexplored, which means the true scale of Titania's geological features may be even larger than we currently know. And that leaves scientists with a fascinating possibility. Titania may still be hiding secrets beneath its frozen crust. And that mystery leads to an even bigger question. Because if Titania once had enough internal heat to fracture its entire surface, what else might still be hidden deep inside this distant moon? In the next part, we explore the internal structure of Titania and whether this frozen world may once have contained a hidden ocean beneath its ice. Far from the warmth of the inner solar system, Titania continues its quiet orbit around Uranus, moving through a region of space where sunlight is faint and temperatures remain brutally cold. From a distance, it looks like a frozen relic of the solar system's early history, a moon whose surface has remained mostly unchanged for billions of years. Yet the enormous canyons carved across Titania's crust tell a very different story. These giant fractures suggest that Titania was once far more dynamic than it appears today. At some point in its past, something inside the moon must have generated enough energy to stretch and tear its surface apart. Understanding what caused this transformation requires looking not at Titania's surface, but deep inside the moon itself. Like many medium-sized moons in the outer solar system, Titania is believed to be made primarily from a mixture of water ice and rocky material. Studies of its density suggest that roughly half of Titania's mass is rock, while the other half is made of frozen water and other ices. This mixture is common among icy moons that formed in the colder outer regions of the solar system billions of years ago. But Titania is large enough that gravity would have gradually pulled its heavier materials inward. Over time, this process, known as differentiation, may have separated the moon into layers. At the center of Titania, there may be a rocky core, surrounded by a thick mantle of ice. Above that icy mantle lies the moon's outer crust, which is what we see today when spacecraft photograph its surface. If Titania did undergo this internal separation, it raises an intriguing possibility. Between the rocky core and the icy outer shell, there could once have existed a layer of liquid water. In other words, Titania may once have possessed a subsurface ocean hidden deep beneath its frozen exterior. At first, this idea might sound surprising. After all, Titania orbits extremely far from the Sun. Temperatures are so low that even nitrogen and methane can freeze solid. How could liquid water possibly exist inside a moon this cold? The answer lies in the early history of the solar system. When moons first form, they often contain a variety of radioactive elements mixed within their rocky material. These elements slowly decay over time, releasing heat in the process. In larger moons, this heat can accumulate inside the interior. Billions of years ago, when Titania was newly formed, the concentration of radioactive elements inside its rocky core may have produced enough heat to partially melt the surrounding ice. This process could have created pockets or layers of liquid water trapped beneath the crust. But radioactive decay may not have been the only heat source. Another powerful force could have contributed to Titania's internal warming: gravitational interactions with Uranus and neighboring moons. In many planetary systems, moons can experience a process called tidal heating. As a moon orbits its planet, gravitational forces stretch and compress the moon slightly during each orbit. This repeated flexing generates heat inside the moon's interior. A famous example of this process occurs on Jupiter's moon Io, the most volcanically active world in the solar system. Io's intense volcanic activity is driven by powerful tidal forces from Jupiter and its neighboring moons. Titania does not experience tidal heating anywhere near as strong as Io's, But even a small amount of tidal flexing early in its history could have helped warm its interior. Combined with radioactive heating, this may have been enough to melt significant amounts of ice within the moon. If Titania did develop an internal ocean, its crust would have behaved very differently than it does today. Instead of being a rigid shell of solid ice, the outer crust would have floated on top of a layer of liquid water. This could allow the crust to shift, fracture, and slowly deform over time. But the most dramatic changes may have occurred later, because internal oceans inside icy moons do not always last forever. As time passes and internal heat gradually fades, these oceans can begin to freeze solid, and when water freezes, something unusual happens. It expands. On Earth, this expansion is responsible for the familiar phenomenon of water pipes bursting in winter when the water inside them freezes. Ice takes up more space than liquid water. Inside a moon like Titania, the freezing of a global subsurface ocean would create enormous pressure. As the ocean slowly turned into solid ice, it would push outward against the moon's crust. This expansion could stretch the crust beyond its limits, causing it to crack open along enormous fractures. These fractures could eventually grow into the massive canyon systems we see today. In other words, Titania's giant valleys may be the scars left behind by a planet-wide freezing event that occurred billions of years ago. The evidence supporting this idea can be seen in the structure of Titania's canyons. Many of them appear to be graben formations, a geological structure created when a block of crust drops downward between two parallel faults. This kind of terrain forms when the crust is pulled apart. On Earth, similar features appear in tectonic regions where the planet's crust is stretching. On Titania, the same type of stretching may have occurred as the moon's interior expanded during the freezing of an ancient ocean. Some of Titania's canyons are estimated to be several kilometers deep, with towering walls of ice rising above the valley floors. If a spacecraft were to fly through one of these valleys, it would see cliffs of frozen water towering thousands of meters high on either side. And these valleys extend for astonishing distances. Messina Chasma, the largest canyon system on Titania, stretches across much of the moon's surface. If it were placed on Earth, it would run across entire continents. But Titania's geological history may not be limited to fractures alone. Voyager 2's images revealed other curious features on the moon's surface that hint at past geological activity. In several regions, scientists observed smooth plains that appear to have fewer impact craters than the surrounding terrain. This suggests that these areas may have formed later in Titania's history. One possibility is that these plains were created by cryovolcanism. Cryovolcanoes are similar to ordinary volcanoes, but instead of erupting molten rock, they release mixtures of water, ammonia, and other volatile materials that behave like liquids in extremely cold environments. When these substances erupt onto the surface of an icy moon, they can spread out and freeze into smooth layers. Several moons in the outer solar system show evidence of cryovolcanic activity. Saturn's moon Enceladus actively ejects plumes of water vapor from beneath its crust, while Pluto's moon Charon displays large, smooth regions that may have formed from ancient cryovolcanic flows. Titania may have experienced similar activity long ago. If cracks in the moon's crust allowed liquid water or slushy ice from the interior to reach the surface. These materials could have flowed across the landscape before freezing solid. Over time, these frozen flows would smooth out the terrain and cover older impact craters. This could explain why some regions of Titania appear younger than others. But Voyager 2's flyby provided only a brief glimpse of this distant world. The spacecraft passed Uranus quickly, capturing images for only a short period before continuing its journey deeper into the solar system. Because of this, scientists have detailed images of only about 40% of Titania's surface. The remaining 60% remains largely unseen. This means there could be enormous geological structures on the far side of Titania that we have never observed. There could be canyon systems even larger than Messina Chasma. There could be cryovolcanic plains covering vast regions. Or there could be entirely new geological features that scientists have not yet imagined. Unfortunately, since Voyager 2's flyby in 1986, no spacecraft has returned to Uranus. For nearly 4 decades, Titania has remained unexplored. But that may soon change. In recent years, planetary scientists have begun pushing for a new mission to the Uranus system. Such a mission would send a spacecraft into orbit around the ice giant, allowing it to study Uranus and its moons in far greater detail than ever before. If such a mission is approved, Titania would almost certainly be one of its most important targets, because despite its quiet appearance, Titania may hold crucial clues about how icy worlds evolve. Understanding Titania's geological history could help scientists answer much larger questions. How common are subsurface oceans inside icy moons? How long can those oceans survive? And under what conditions might they persist for billions of years? These questions are important not only for understanding Titania, but also for understanding the many icy worlds scattered throughout our solar system. Because if liquid water once existed beneath Titania's crust, it raises a fascinating possibility. Even in the cold outer regions of the solar system, hidden oceans may once have been far more common than we once believed. And Titania's frozen canyons may be the silent evidence of that ancient hidden world buried beneath the ice. Even though Titania appears quiet and frozen today, the immense canyon systems that scar its surface suggest that this moon once experienced dramatic geological change. But to understand how Titania evolved into the world we see today, scientists must look further back, all the way to the formation of the Uranus system itself, more than 4 billion years ago. During the earliest period of the solar system's history, planets and moons were forming from vast clouds of gas, dust, and ice left over from the birth of the Sun. In the outer regions of the solar system, where temperatures were extremely low, icy materials could easily condense and accumulate. This allowed large icy worlds to form around the giant planets. Uranus likely formed from a growing core of rock and ice that gradually pulled surrounding material toward it through gravity. As Uranus grew larger, a swirling disk of debris formed around the young planet. Within this disk, smaller clumps of ice and rock began sticking together. Over time, these clumps collided, merged, and slowly grew into the moons that orbit Uranus today. Titania was probably one of the largest objects to form within this ancient disk. Because it gathered large amounts of material, Titania became massive enough for gravity to shape it into a nearly perfect sphere. This spherical shape indicates that the Moon reached a size where its internal gravity could overcome the strength of the materials inside it, pulling everything into equilibrium. But the early solar system was not a peaceful place. It was chaotic and violent. Asteroids and comets frequently collided with planets and moons, leaving behind enormous craters and reshaping the surfaces of these worlds. Titania was no exception. In fact, many of the impact craters visible on Titania today date back to this early era known as the Late Heavy Bombardment, a period roughly 4 billion years ago, when impacts were extremely common throughout the solar system. Some of the craters on Titania are truly enormous. Certain impact basins stretch hundreds of kilometers across, indicating collisions with objects many kilometers wide. These impacts would have released tremendous amounts of energy, temporarily melting ice and rock and possibly reshaping large regions of the Moon's surface. But these collisions may have done more than just create craters. They may have influenced Titania's internal evolution as well. Large impacts can generate significant heat. When massive asteroids strike an icy moon, the energy released can melt surrounding ice and create temporary pockets of liquid water beneath the surface. If Titania experienced several large impacts early in its history, these events could have contributed to warming the Moon's interior and accelerating the formation of internal layers. Over time, Titania may have developed a rocky central core surrounded by an icy mantle, with possible pockets of liquid water forming between these layers. If such internal oceans existed, they would not necessarily remain stable forever. The interior of a moon gradually cools as heat escapes into space. As this cooling occurs, liquid water trapped beneath the crust eventually begins to freeze. But as discussed earlier, freezing water expands. This expansion creates enormous outward pressure on the surrounding crust. The result may have been the massive tectonic fractures that cut across Titania's surface today. However, Titania's geology may have been influenced by another powerful force: the unusual tilt of Uranus itself. Unlike any other planet in the solar system, Uranus rotates almost completely on its side. Its axis is tilted by about 98 degrees, meaning the planet essentially rolls around the Sun rather than spinning upright like Earth or Jupiter. Scientists believe this extreme tilt was caused by a massive collision early in Uranus's history. At some point during the formation of the solar system, a large protoplanet, possibly several times the mass of Earth, may have slammed into Uranus. The impact would have been powerful enough to knock the entire planet sideways. Such a collision would have had enormous consequences for the Moon's orbiting Uranus. The gravitational environment around the planet would have changed dramatically. Some moons may have been destroyed entirely, while others may have been thrown into new orbits. Titania itself could have experienced strong gravitational disturbances during this event. These disturbances might have temporarily increased tidal forces acting on the Moon, creating additional internal heating. If Titania's interior was already partially melted at the time, this extra energy could have further destabilized the crust, helping to generate the enormous fractures we see today. In this sense, Titania's canyon systems may be indirectly connected to one of the most violent events in the history of the Uranus system. But even after these dramatic events, Titania eventually began to cool. As billions of years passed, the Moon gradually lost much of its internal heat. Geological activity slowed, and the once dynamic processes that reshaped its surface faded away. The freezing of Titania's interior likely continued for millions of years. During this time, the expanding ice beneath the surface would have continued pushing against the crust, gradually widening the fractures that had already formed. Sections of the crust may have dropped downward along fault lines, creating the deep valleys that remain visible today. Once this freezing process was complete, Titania would have become far more stable. Its crust hardened into a thick, rigid shell of ice and rock. Without significant internal heat, the Moon's geological activity effectively stopped. Since then, Titania has existed largely unchanged, drifting silently through space, while the rest of the solar system continued evolving around it. Yet Titania still retains a surface that tells the story of its past. Impact craters record the violent early era of planetary formation. Gigantic canyon systems reveal the internal forces that once reshaped the Moon's crust. And smooth plains hint at the possibility of ancient cryovolcanic flows that may have resurfaced parts of the landscape. Together, these features paint the picture of a Moon that was once far more active than its quiet appearance suggests. But Titania's story may not be finished, because scientists are beginning to suspect that the interiors of icy moons can remain warmer than expected for extremely long periods of time. Recent studies of other moons in the outer solar system have shown that subsurface oceans can persist for billions of years under the right conditions. Europa and Enceladus are famous examples, but they may not be unique. Even distant moons like Titania could potentially retain small pockets of liquid water deep beneath their frozen surfaces. If such pockets exist, they would be incredibly difficult to detect from afar. Only a spacecraft equipped with advanced instruments, capable of measuring gravitational variations and magnetic signals, could determine whether Titania still hides liquid water beneath its crust. This is one of the reasons why scientists are eager to return to the Uranus system. A future mission could map Titania's surface in far greater detail, revealing geological features that Voyager 2 was unable to see. Radar instruments might even be able to probe beneath the icy crust, searching for hidden layers of liquid water. If evidence of such an ocean were discovered, Titania would suddenly become far more interesting than anyone expected. Because wherever liquid water exists, scientists begin asking another profound question. Could environments like this potentially support the chemistry required for life? At first glance, Titania may seem like an unlikely place for life to exist. Its surface is extremely cold and exposed to the harsh environment of space. But beneath its crust, conditions could be very different. Protected from radiation and insulated by thick layers of ice, a subsurface ocean could remain stable for millions or even billions of years. On Earth, life has been discovered thriving in some of the most extreme environments imaginable. Deep beneath the ocean floor, inside volcanic vents, and even within Antarctic ice. These discoveries have dramatically changed scientists' understanding of where life might be able to exist. And they have forced researchers to reconsider icy worlds like Titania. While there is currently no direct evidence, that Titania contains liquid water today. Its geological history suggests that such conditions may have existed in the past. If future missions confirm that Titania once possessed an ocean beneath its crust, it would add another fascinating piece to the puzzle of how icy moons evolve. But until a spacecraft returns to Uranus, Titania remains a distant and mysterious world, a frozen moon scarred by enormous canyons, a silent witness to billions of years of solar system history. And perhaps, deep beneath its icy surface, a world that once held far more activity than we ever imagined. Although Titania appears quiet and frozen today, its surface still preserves clues that allow scientists to reconstruct the dramatic history of this distant moon. Every crater, valley, and fracture tells a story about the forces that shaped it over billions of years. By studying these features carefully, researchers can slowly piece together the events that transformed Titania from a young icy world into the fractured landscape we observe today. One of the most important clues comes from the distribution of impact craters across Titania's surface. Impact craters form when asteroids or comets collide with the moon at extremely high speeds. These collisions release enormous amounts of energy, blasting out huge circular depressions and scattering debris across the surrounding terrain. Over long periods of time, the number of craters on a surface can reveal how old that surface is. If a region contains many craters, it usually means that the surface has remained unchanged for billions of years. But if a region contains fewer craters, it may indicate that geological activity has resurfaced the area more recently, erasing older impact marks. On Titania, scientists noticed something interesting. Some regions of the moon are heavily cratered, suggesting that these areas have remained largely untouched since the early days of the solar system. Other regions, however, appear smoother and contain far fewer craters. This uneven distribution suggests that Titania's surface did not form all at once. Instead, different regions may have formed or been modified at different times. One explanation for this pattern involves the enormous canyon systems that stretch across the moon. When Titania's crust fractured and sections of it pulled apart, some regions may have shifted downward while others remained elevated. These movements could have exposed fresh layers of ice from beneath the surface. Once exposed, these newer surfaces would begin accumulating impact craters from scratch. As a result, areas near the canyon systems may appear younger than the surrounding terrain. This type of geological process is known as tectonic resurfacing, and it is similar in some ways to the movement of tectonic plates on Earth. Of course, Titania does not have plate tectonics like our planet. Its crust is far too thick and cold for large plates to move freely across the surface. But localized stretching and fracturing of the crust can still reshape large regions over time. The canyons on Titania are some of the most dramatic examples of this process anywhere in the solar system. Many of these fractures run in long, straight lines across the moon's surface, indicating that powerful stresses once acted on Titania's crust. In some places, the crust appears to have been pulled apart so strongly that entire sections dropped downward, forming deep valleys. These valleys are known as rift valleys, and they form where the planetary crust is stretched until it breaks. On Earth, similar structures can be found in places like the East African Rift Valley, where tectonic forces are slowly pulling the African continent apart. On Titania, however, the forces responsible for these fractures likely came from inside the Moon, rather than from moving tectonic plates. As the Moon's interior cooled and expanded during the freezing of a possible subsurface ocean, enormous stresses would have built up within the crust. Eventually, the crust could no longer withstand these forces and began to crack. These cracks widened over time, eventually forming the gigantic canyon systems visible today. But Titania's canyons may not be the only evidence of internal activity. Scientists have also identified several bright streaks and deposits on the Moon's surface that appear to have originated from inside the crust. Some of these features look like material that flowed outward from fractures before freezing solid. This suggests that liquid or semi-liquid substances may once have reached the surface through cracks in the crust. If this interpretation is correct, Titania may have experienced cryovolcanic eruptions long ago. Cryovolcanism is a process similar to ordinary volcanism, but instead of molten rock, the eruptions involve mixtures of water, ammonia, methane, or other volatile substances. Because these materials remain liquid at extremely low temperatures, they can erupt onto the surface of icy moons, even in the cold outer solar system. When these substances spread across the surface and freeze, they create smooth plains and bright deposits that stand out against the surrounding terrain. Evidence of cryovolcanism has already been observed on several other icy worlds, including Enceladus, Triton, and Pluto. Titania may have experienced similar activity billions of years ago. If cracks in the crust allowed subsurface liquids to escape, these materials could have flowed along the canyon floors before freezing solid. Over time, repeated eruptions might have gradually resurfaced certain regions, covering older craters and creating smoother landscapes. Another intriguing feature of Titania's surface is its subtle, reddish coloration. Images from Voyager 2 showed that Titania's ice is not pure white. Instead, much of the surface has a faint, reddish tint. This coloration likely comes from complex organic molecules that have accumulated on the surface over time. In the outer solar system, radiation from the Sun and energetic particles trapped within planetary magnetic fields can interact with frozen materials on the surfaces of moons. These interactions can break apart simple molecules like methane and water, allowing them to recombine into more complex organic compounds. Over millions of years, these compounds gradually darken and redden the surface of icy worlds. Titania's reddish color suggests that its surface has been exposed to space for extremely long periods without significant renewal. If active geological processes were still occurring today, they would likely expose fresh ice and brighten the surface. But Titania's muted coloration implies that the Moon has remained relatively inactive for billions of years. Despite this long period of quiet stability, Titania's position within the Uranus system still exposes it to interesting environmental effects. Unlike many other planetary systems, Uranus possesses a very unusual magnetic field. Most planetary magnetic fields are roughly aligned with the planet's rotation axis. Earth's magnetic field, for example, emerges near the geographic poles. But Uranus is different. Its magnetic field is both tilted and offset from the planet's center. This means that as Uranus rotates, its magnetic field sweeps through space in an unusual pattern. Moons orbiting the planet pass through regions of varying magnetic intensity as they travel around Uranus. Titania experiences this constantly changing magnetic environment during each orbit. Charged particles trapped within Uranus's magnetosphere occasionally strike Titania's surface, slowly altering the chemistry of the ice. Over time, this radiation can darken surface materials and produce the organic compounds responsible for Titania's reddish color. These interactions also contribute to the gradual erosion of the Moon's surface. Microscopic impacts from charged particles slowly break down surface ice, releasing molecules into space and subtly reshaping the outermost layers of the Moon. Although these processes occur extremely slowly, they continue even today. In this sense, Titania is not completely inactive. Even though its interior may have cooled billions of years ago, its surface is still being influenced by the environment of the Uranus system. But the biggest limitation in understanding Titania remains the lack of detailed observations. Voyager 2's flyby provided only a brief snapshot of this distant moon. Its cameras captured remarkable images, but the spacecraft was moving quickly and had limited time to study each moon in detail. As a result, much of Titania's surface remains poorly mapped. Entire regions of the Moon have never been photographed at high resolution. Scientists suspect that Titania may contain additional canyon systems, impact basins, and geological features that have never been observed. Future missions to the Uranus system could transform our understanding of Titania. A spacecraft placed into orbit around Uranus could repeatedly fly past Titania, mapping its entire surface in detail. High-resolution cameras could reveal smaller geological features that Voyager 2 was unable to detect. Spectrometers could analyze the chemical composition of Titania's surface, identifying the materials that make up its icy crust. And, perhaps most exciting of all, radar instruments might be able to probe beneath the surface. By sending radio waves into Titania's crust and measuring the signals that bounce back, scientists could determine whether hidden layers of liquid water still exist deep below the ice. Such a discovery would dramatically change how we view Titania. Instead of a completely frozen and inactive world, Titania could turn out to be another member of the growing family of ocean worlds in our solar system. For now, however, Titania remains a distant mystery, a moon shaped by ancient fractures, a world whose frozen valleys stretch for thousands of kilometers, and a silent reminder that even in the coldest regions of the solar system, planetary bodies can undergo dramatic transformations that leave their marks for billions of years. For most of its existence, Titania has remained far from the attention of spacecraft and astronomers. Compared to famous worlds like Europa, Titan, or Enceladus, Titania rarely appears in discussions about the most fascinating moons of the solar system. Yet the more scientists study the limited data available from Voyager 2, the more they realize that this distant moon may hold important clues about the evolution of icy worlds. One of the most striking aspects of Titania is its size. Among the moons of Uranus, Titania is the largest. With a diameter of about 1,578 kilometers, it is large enough for gravity to have shaped it into a nearly spherical body. This size places Titania in an interesting category of moons. It is larger than many small irregular satellites, but smaller than the truly massive moons like Jupiter's Ganymede or Saturn's Titan. This intermediate size is important because it determines how much internal heat the moon could retain during its early history. Smaller moons tend to cool quickly. Because their interiors are relatively small, heat escapes easily into space, leaving them geologically inactive. Larger moons, however, can trap heat inside for much longer periods of time. This allows internal processes such as tectonics, volcanism, or subsurface oceans to develop. Titania lies near the boundary between these two categories. It is just large enough that its interior may once have remained warm for hundreds of millions of years after formation. During that time, the internal heat generated by radioactive elements within its rocky core could have slowly warmed the surrounding ice. If this warming was strong enough, parts of the ice mantle could have melted, creating pockets of liquid water beneath the surface. This possibility has fascinated scientists because subsurface oceans are becoming increasingly important in planetary science. In recent decades, discoveries across the solar system have shown that hidden oceans may exist on many icy moons. Europa, orbiting Jupiter, is perhaps the most famous example. Beneath its icy crust lies a global ocean containing more water than all of Earth's oceans combined. Evidence for this ocean comes from measurements of Europa's magnetic field and observations of its fractured surface. Saturn's moon Enceladus has also revealed clear evidence of liquid water. Jets of water vapor erupt from fractures near its south pole, forming enormous plumes that spray ice particles into space. Even Pluto's moon Charon may have once possessed an internal ocean that froze long ago, leaving behind enormous fractures similar to those seen on Titania. These discoveries suggest that subsurface oceans may be far more common than scientists once believed. If Titania once contained such an ocean, it would help explain the massive canyon systems stretching across its surface. When water freezes, it expands by roughly 9%. In a confined space beneath a thick crust, this expansion could create enormous stress within the outer shell. Imagine a sealed container filled with water slowly freezing from the inside. As the ice forms, it presses outward against the walls of the container. If the pressure becomes strong enough, the container eventually cracks. On Titania, the same principle may have occurred on a planetary scale. As a hidden ocean beneath the crust gradually froze, the expanding ice could have pushed outward against the moon's outer shell. Over time, the crust would have stretched and fractured, producing the vast canyon systems visible today. But the story may be even more complex, because Titania is not the only moon in the Uranus system with signs of tectonic activity. Another moon, Oberon, also shows evidence of large fractures and valleys across its surface. Although Oberon's features are less dramatic than Titania's canyons, their existence suggests that several of Uranus's moons may have experienced similar internal processes. This raises an intriguing possibility. Perhaps the entire Uranus system once contained more internal heat than it does today. If the moons formed from similar materials within the same disk around Uranus, they may have shared similar internal structures. Over time, differences in size and composition would have influenced how each moon evolved. Titania, being the largest, may have retained internal heat longer than its neighbors. This would allow geological activity to persist for a longer period, producing the massive canyon systems we see today. Oberon, slightly smaller, may have experienced similar processes but on a smaller scale. Meanwhile, smaller moons such as Ariel and Umbriel show their own unique geological features that hint at complex histories. Together, these moons form a miniature laboratory for studying how icy worlds evolve over billions of years. But Titania's story may not be entirely confined to the past. Some researchers have suggested that residual heat could still exist deep within the moon's interior. Although the majority of Titania's internal heat likely dissipated long ago, certain conditions might allow small pockets of warmth to remain trapped beneath the crust. For example, if Titania's icy mantle contains substances such as ammonia, the freezing point of water could be lowered significantly. Water mixed with ammonia can remain liquid at much lower temperatures than pure water. This means that even in extremely cold environments, small layers of liquid could persist beneath thick ice shells. Such mixtures are thought to exist on several icy moons throughout the outer solar system. If Titania's interior contains similar compounds, it is possible that small regions of liquid water might still exist beneath the crust today. Detecting such hidden layers would require precise measurements from a spacecraft orbiting Uranus. One method scientists use to search for subsurface oceans involves measuring subtle changes in a moon's gravitational field. If a moon contains a liquid layer beneath its crust, that layer can shift slightly as the moon orbits its planet. These tiny movements alter the moon's gravitational pull, which can be detected by instruments aboard nearby spacecraft. Another technique involves studying magnetic fields. Liquid water containing dissolved salts conducts electricity. If a subsurface ocean exists beneath Titania's crust, it could interact with Uranus's magnetic field, producing detectable signals. Similar methods have already been used to confirm the existence of subsurface oceans on Europa and Ganymede, but so far, Titania has never been studied with instruments capable of making these measurements. Since Voyager 2's brief flyby in 1986, no spacecraft has returned to the Uranus system. For decades, Uranus has remained one of the least explored planets in the solar system. Yet that situation may soon change. Planetary scientists have increasingly argued that the Uranus system should be a priority for future exploration. In fact, recent studies by space agencies have ranked a Uranus orbiter mission among the most important future missions in planetary science. Such a mission would send a spacecraft into orbit around Uranus, allowing scientists to study the planet and its moons in unprecedented detail. The spacecraft could perform multiple flybys of Titania, gradually building a complete map of its surface. Advanced instruments could measure Titania's gravitational field, analyze its surface chemistry, and search for signs of internal oceans. Radar systems might even penetrate the icy crust, revealing hidden layers beneath the surface. These observations would transform Titania from a mysterious distant moon into a well-understood planetary world, and the discoveries could extend far beyond Titania itself. Understanding Titania's geological history would help scientists learn how medium-sized icy moons evolve throughout the solar system. Such knowledge could also apply to the many icy worlds orbiting other planets, both in our solar system and around distant stars, because Titania represents a type of world that may be extremely common in the universe. A frozen moon with a mixture of rock and ice. A world shaped by internal heat and ancient tectonic forces. A place where hidden oceans may once have existed beneath the surface. And although Titania currently appears silent and inactive, the scars carved across its icy crust suggest a far more dramatic past. The enormous canyon systems stretching across the moon remain as reminders of the powerful forces that once reshaped this distant world. They are the frozen traces of a time when Titania was not merely a quiet satellite drifting around Uranus, but a dynamic world undergoing profound transformations deep beneath its icy shell. Titania's Great Canyons are among the most dramatic surface features in the Uranian system, but they do more than make the moon visually striking. They suggest that, at some point in its history, Titania underwent a major internal transformation. A moon does not simply tear itself apart without a cause. Something beneath the surface had to push outward with enough force to stretch the crust across enormous distances. And once scientists realized that, Titania stopped looking like a quiet, frozen world and started looking like the remains of a much more active past. To understand what happened, it helps to imagine Titania not as it appears today, but as it may have existed billions of years ago. When Titania first formed, the solar system was a far more violent place. Uranus was still young, the leftover material around it was still settling, and impacts were common. In that early era, moons like Titania would have formed from a mixture of rock and ice orbiting around the growing planet. As material collided and merged, Titania gradually increased in size until its own gravity pulled it into a roughly spherical shape. That early Titania would not have been completely frozen through. Even though it formed far from the sun, several heat sources could have warmed its interior. The first source was the heat left over from its formation itself. Every collision that added material to the growing moon also released energy. The second source was radioactive decay inside its rocky material. Certain elements naturally release heat over time, and in a body large enough to trap some of that warmth, temperatures deep inside can rise significantly. The third possible source was tidal interaction with Uranus, especially if Titania's orbit in the distant past was slightly more elliptical than it is now. Together, these sources may have been enough to partially melt the moon's icy interior. If that happened, Titania may have developed a layered structure, a rocky core at the center, an icy mantle above it, and perhaps, between the deep interior and the outer crust, a layer of liquid water mixed with ammonia or salts. These compounds matter because they lower the freezing point of water. In other words, Titania would not need Earth-like warmth to maintain a hidden ocean. Under the right chemical conditions, liquid could survive far below zero, sealed beneath many kilometers of ice. This is where the giant canyons begin to make sense. If Titania once held a subsurface ocean, and if that ocean gradually froze over time, the freezing process would have changed the moon's volume. Water expands when it becomes ice. On Earth, this is why freezing water can crack stone or split pipes. On Titania, the same principle could have acted on a planetary scale. As the internal ocean froze, it would expand and push against the crust above it. The outer shell would slowly be forced outward until it reached its structural limit. Then it would crack. Those cracks would not remain small. Under enough stress, entire sections of crust could pull apart, creating long fault valleys and chasms. Some portions of the surface would sink between parallel fractures, forming deep canyon floors bordered by steep walls. Over immense timescales, these structures could grow into the enormous systems we now identify as Titania's defining geological features. One of the best known of these is Messina Chasma, a vast fault valley extending across a major portion of the Moon's visible surface. It is not just a small crack or local fracture. It is a sign that Titania's crust was once under global stress. The same is true for other chasmata on the Moon. Their scale suggests that the event responsible was not isolated. Titania may have gone through a moon-wide tectonic phase, where internal expansion affected enormous regions of the crust. And this raises another question. If Titania once had enough heat to sustain internal liquid, and if that liquid later froze and split the crust open, how long did that process take? The answer was almost certainly not sudden. Titania's transformation would have unfolded over millions of years. Heat would gradually leak out into space. The interior ocean would freeze slowly from the top and bottom. Pressure would build incrementally beneath the crust. Fractures might form in stages, with some regions opening earlier than others. Some canyons could be older than others, reflecting different phases of internal cooling. Titania's surface, in other words, may preserve a long tectonic history rather than a single catastrophic event. Voyager 2 gave us only a partial view of this story. When the spacecraft flew past Uranus in 1986, it captured just one hemisphere of Titania in detail. That hemisphere revealed the Moon's great canyons, but it left much of the world unseen. The far side remains poorly known. It is entirely possible that additional canyon systems, fault blocks, or resurfaced plains exist there, waiting to be discovered. Titania's full geological story remains incomplete simply because we have not yet looked closely enough. Still, even from the limited images, another important clue becomes clear. Some areas of Titania appear smoother and less cratered than others. This matters because craters accumulate over time. A heavily cratered surface is usually old. A smoother surface may be younger, or at least may have been modified after the oldest impact era. On Titania, these smoother areas could indicate that some geological process altered parts of the crust after the Moon's earliest craters had already formed. One possibility is tectonic resurfacing linked to canyon formation. When faulting occurs, it can expose fresher subsurface material along canyon walls and floors. Another possibility is cryovolcanism. If water-ammonia mixtures or slushy ice reach the surface through fractures, they may have spread across low areas and frozen into smooth plains. Titania does not show active plumes like Enceladus, and there is no evidence of modern eruptions, but ancient cryovolcanism remains a serious possibility. If that happened, then Titania was not merely cracking open. It may also have been leaking material from within. That would make Titania even more geologically interesting. Instead of being a simple, frozen block of ice and rock, it would have been a moon with a complex internal evolution. Heating, melting, differentiation, tectonic fracturing, and possibly cryovolcanic resurfacing, All of this on a world orbiting nearly 3 billion kilometers from the Sun. And yet, today, Titania appears silent. The canyons remain, but they no longer widen. The crust is fractured, but no fresh movements have been observed. The hidden ocean, if it ever existed, is likely gone or reduced to isolated pockets deep below the surface. The moon has cooled. Geological activity has faded. What remains is the fossil record of processes that ended long ago. That is what makes Titania so compelling. It is not active in the dramatic way Io is active, with giant volcanic eruptions. It is not obviously venting water into space like Enceladus. Its mystery is quieter. Titania asks scientists to reconstruct a lost past from frozen clues. Its giant canyons are the visible remains of forces we can no longer observe directly. They are geological memories preserved in ice. And those memories may be incredibly important for understanding not only Titania, but icy worlds in general. Across the solar system, scientists are increasingly finding evidence that oceans, internal heat, and tectonic activity may be common among icy moons. Some of these worlds are small. Some are enormous. Some, like Europa and Enceladus, are active today. Others, like Titania, may represent a later stage, worlds where the ocean has frozen, the heat has faded, and only the tectonic scars remain. By studying Titania, scientists can learn what happens after an ocean world grows old. That question matters because it helps place more famous moons into a larger timeline. Europa today may be active, but will it one day resemble Titania? Did Titania once pass through a stage similar to the one Europa occupies now? Could frozen tectonic canyons across the solar system be the remains of dead or dying ocean worlds? We do not yet know. Answering those questions will require returning to Uranus. A future orbiter could map Titania's entire surface, measure its gravity field, probe its crust, and search for signs of internal structure. It could tell us whether the canyon systems are globally connected, whether smoother plains really are cryovolcanic, and whether any liquid still survives in the deep interior. It could finally show us the unseen hemisphere and reveal whether the visible side was typical or exceptional. Until then, Titania remains suspended between what we know and what we suspect. We know it is the largest moon of Uranus. We know its surface holds giant hidden canyons. We know those canyons point to a past shaped by internal forces, but much of the story remains buried beneath ice, distance, and time. What Voyager showed us was enough to change Titania from a forgotten moon into a serious geological mystery. And the deeper scientists look at those frozen canyons, the harder it becomes to see Titania as a simple, lifeless world. Because beneath that silent crust may lie the remains of an ancient ocean, and across its surface are written the scars of the day that ocean began to die. Far beyond the orbit of Saturn, beyond the storms of Jupiter, and far beyond the familiar warmth of the Sun, Uranus quietly circles the darkness, and around this distant world travels Titania, the largest moon of the Uranian system. From far away, Titania appears calm and silent, a frozen sphere drifting endlessly through space. But when scientists began studying its surface more closely, they discovered something unexpected. Titania is not smooth. It is cracked, broken, and scarred by a violent past. A world covered in ice and stone. Titania's surface is dominated by water ice mixed with dark, rocky material. Temperatures here are incredibly low, around minus 203 degrees Celsius, minus 333 degrees Fahrenheit. At such extreme cold, water behaves more like solid rock than ice. It becomes hard, brittle, and capable of fracturing in dramatic ways. Over billions of years, Titania's frozen crust has cracked apart, creating enormous valleys, cliffs, and deep fractures across its surface. These geological scars tell the story of a moon that was once far more active than it appears today. Giant valleys across the moon. One of Titania's most striking features is its network of massive canyons. Some of these valleys stretch hundreds of kilometers across the surface. They resemble the great rift valleys seen on Earth or Mars. But on Titania, they formed under completely different conditions. These valleys are known as graben structures. A graben forms when a section of crust collapses downward between two large faults. This happens when a planet or moon expands internally, stretching its outer shell until it fractures. Titania appears to have experienced this exact process. Long ago, something inside Titania pushed outward, stretching the icy crust until it cracked apart. The result was a landscape filled with enormous tectonic scars. Messina Chasma, Titania's giant canyon. Among Titania's most famous features is a vast canyon called Messina Chasma. This canyon is enormous. It stretches for more than 1,500 kilometers across the moon's surface. For comparison, that is roughly the distance from New York to Denver. And the cliffs inside Messina Chasma plunge several kilometers deep. Imagine standing at the edge of such a canyon. The walls of frozen ice would tower above you like frozen mountains. The valley floor would stretch into the darkness, and overhead, Uranus would hang in the sky, tilted sideways, glowing faintly in the distance. It would be one of the most alien landscapes imaginable. Why did Titania crack? Scientists believe Titania's fractures formed during a dramatic period early in its history. When Titania first formed billions of years ago, it was likely warmer inside. Heat from radioactive elements in its rocky interior may have slowly warmed the moon's internal layers. This heat could have melted some of Titania's internal ice, creating a subsurface ocean of liquid water. As that internal ocean later began to freeze, the water expanded. And when water freezes, it increases in volume. This expansion would have pushed outward against Titania's crust. The icy surface could no longer contain the pressure, and so it cracked. Massive fractures opened across the moon. Gigantic valleys formed, and Titania's surface permanently changed. A landscape frozen in time. Unlike Earth, Titania has no atmosphere, no rain, and no wind. That means once these valleys formed, they stayed almost exactly the same for billions of years. Nothing erodes them, nothing fills them in. Titania is essentially a cosmic fossil, a snapshot of ancient geological activity preserved in ice. Every canyon, ridge, and fracture is a piece of Titania's ancient history. A frozen memory of a time when the moon was far more dynamic. The impact craters of Titania. Alongside its valleys, Titania's surface is also covered in impact craters. These craters formed when asteroids and comets struck the moon over billions of years. But interestingly, Titania does not have as many craters as some other icy moons. This suggests something important. At some point in Titania's past, parts of its surface were renewed or reshaped. Large tectonic fractures may have erased older craters, or internal activity may have slowly resurfaced sections of the Moon. This means Titania was not always the quiet, frozen world we see today. Long ago, it may have been far more active. A surface of two worlds. Titania's surface appears to have two main types of terrain. The first type is heavily cratered, ancient, and extremely old. These regions likely date back nearly 4 billion years. The second type includes the large valleys and tectonic fractures. These areas appear younger, formed after Titania's interior expanded and cracked the crust. This tells scientists that Titania experienced multiple geological eras. First came the intense bombardment period when craters formed everywhere. Then later came the tectonic era, when Titania's crust split apart. After that, the Moon slowly became quiet again. Frozen cliffs and escarpments. Some of Titania's fractures created enormous cliffs called scarps. These cliffs can rise several kilometers high. Because Titania's gravity is weakened only about 4% of Earth's gravity, these cliffs can remain extremely steep without collapsing. If a human stood on Titania, they would weigh only a fraction of their weight on Earth. A 70-kilogram person would feel as light as about 3 kilograms. This low gravity allows Titania's cliffs to tower dramatically over its frozen landscape. Some may be among the tallest icy cliffs in the solar system. The color of Titania. Titania's surface has a slightly reddish color. This coloration likely comes from space weathering. Over billions of years, Titania has been bombarded by tiny particles from the Sun and from Uranus's magnetosphere. These particles slowly alter the chemistry of the ice. They darken it, and sometimes turn it reddish. Scientists also believe Titania's surface may contain complex organic molecules created by radiation interacting with frozen materials. These molecules can tint the ice darker over time. Ice that may not be pure. Spectroscopic observations suggest Titania's ice is not completely clean. It may contain traces of carbon dioxide ice and other frozen compounds. These materials could have originated from Titania's interior. If Titania once had internal oceans or geological activity, gases may have escaped through cracks and frozen on the surface. Over time, radiation from space could transform these chemicals into more complex compounds. This means Titania's surface chemistry may be far richer than it first appears. A world only seen once. Despite its fascinating landscape, Titania remains one of the least explored moons in the solar system. Only a single spacecraft has ever visited Uranus. In 1986, NASA's Voyager 2 flew past the Uranian system. During this brief encounter, Voyager captured the only close images we have of Titania. But the spacecraft could only photograph about 40% of Titania's surface. The rest remains completely unseen. Half of Titania is still a mystery, hidden forever in darkness. The unknown side. The hemisphere of Titania that Voyager never saw may hold entirely new geological features, more valleys, more fractures, perhaps even evidence of ancient cryovolcanic activity, or signs that Titania's interior remained warm longer than scientists once believed. Until another spacecraft returns to Uranus, Titania's hidden side will remain unknown. Waiting for a future mission. Today, scientists are proposing new missions to explore Uranus and its moons. One concept is the Uranus Orbiter and Probe, a mission that could launch in the coming decades. Such a spacecraft would orbit Uranus for years, mapping its moons in detail, studying Titania's geology, searching for signs of subsurface oceans, and finally revealing the secrets of the Uranian system. Titania would become one of the primary targets, because among Uranus's moons, it may hold the most clues about the system's past. A silent monument in the darkness. For now, Titania remains far away, a frozen moon drifting slowly around Uranus, its valleys carved by ancient forces, its cliffs frozen for billions of years, its hidden hemisphere still waiting to be discovered. And in the vast darkness beyond Saturn, Titania continues its quiet orbit, unchanged, unseen, and full of unanswered questions. Far beyond the warmth of the sun, beyond the asteroid belt and the giant storms of Jupiter and Saturn, Uranus drifts slowly through the cold darkness of the outer solar system. And circling this distant planet is Titania, the largest moon of Uranus. At first glance, Titania appears frozen and lifeless, a quiet, icy world locked in deep cosmic silence. But hidden beneath that frozen surface, there may be something extraordinary, something scientists once believed impossible this far from the sun, an ocean, not an ocean like the ones on Earth, but a vast, dark sea trapped deep beneath kilometers of solid ice. And if such an ocean exists, Titania could be far more complex than anyone imagined. The hidden heat of icy worlds. When people imagine icy moons, they often picture them as completely frozen solid. But in the outer solar system, appearances can be misleading. Many moons made primarily of ice actually hide liquid oceans beneath their surfaces. Europa, a moon of Jupiter, contains a global ocean beneath its icy shell. Enceladus, orbiting Saturn, shoots enormous geysers of water vapor into space from cracks near its south pole. Even distant Pluto may contain a buried ocean. These discoveries have transformed how scientists think about icy worlds. They are not just frozen rocks drifting in space. Some may be active worlds with internal heat and hidden oceans. And Titania might belong to this mysterious category. Titania's internal structure. To understand whether Titania could contain an ocean, scientists first try to determine what lies inside the moon. Based on its density and size, Titania is believed to be composed of roughly half ice and half rock. This mixture likely formed when the moon was created billions of years ago from material orbiting Uranus. Over time, Titania's interior probably separated into layers. The heavier rocky materials slowly sank toward the center, forming a dense core. Meanwhile, the lighter icy materials rose upward, forming a thick outer shell. This process is known as differentiation, and it occurs in many planetary bodies. If Titania fully differentiated, its internal structure might look something like this. At the center would be a rocky core. Above that, a thick mantle made of water ice and possibly liquid water. And on top, a frozen crust many kilometers thick. Between those layers, something remarkable could exist. A hidden ocean. Where could an ocean exist? If Titania has an ocean, it would likely lie between the rocky core and the icy crust. This ocean would not be exposed to sunlight. It would exist in total darkness. The water would be trapped beneath kilometers of ice, sealed away from space, and unlike Earth's oceans, it would probably be extremely salty. Salts dissolved in water can lower its freezing temperature. This means that even in the freezing cold of the outer solar system, salty water can remain liquid. Scientists believe this is exactly what may happen inside many icy moons. If Titania's internal ocean contains dissolved salts or ammonia, it could remain liquid for billions of years. Where would the heat come from? But if Titania is so far from the sun, what could possibly keep an ocean from freezing solid? The answer lies deep inside the moon itself. When Titania formed, its rocky interior likely contained radioactive elements. Elements like uranium, thorium, and potassium slowly decay over time, and when they decay, they release heat. This process is called radioactive heating. Even today, billions of years after Titania formed, this slow decay may still generate small amounts of heat inside the moon. It may not sound like much, but over millions of years, that heat could be enough to keep water from freezing completely, especially if salts are present to lower the freezing point. A warm layer. Beneath the ice computer. Models suggest Titania may contain a thin layer of liquid water trapped beneath its icy crust. This ocean would not be enormous like Earth's oceans. Instead, it might be a relatively thin layer, perhaps tens of kilometers thick, but even a thin ocean would be an extraordinary discovery. It would mean Titania is not completely frozen. It would mean the moon still contains active internal processes, and it would place Titania among the growing list of ocean worlds in our solar system. Signs written in Titania's surface. Interestingly, Titania's surface may already contain clues pointing toward such an ocean. Remember the giant fractures and valleys we discussed earlier. Those enormous tectonic cracks may have formed when Titania's interior expanded. If a subsurface ocean froze over time, the water would expand as it turned into ice. This expansion could push outward on the moon's crust, and eventually, the surface would crack open. The vast canyon systems across Titania may be the frozen scars left behind by this expansion. If that is true, Titania's valleys may be the evidence of an ancient ocean slowly freezing inside the moon. Could the ocean still exist today? This is one of the biggest unanswered questions. Did Titania's ocean freeze completely long ago? Or could liquid water still remain beneath the ice today? Some scientists believe the ocean may still survive in a partially liquid state. Even if much of it has frozen, small pockets of liquid water could remain trapped deep inside the moon. These hidden reservoirs might still interact with Titania's rocky core, and if liquid water touches rock, something remarkable can happen. Chemical reactions begin. The possibility of hydrothermal activity. On Earth, many deep-sea ecosystems exist around hydrothermal vents. These vents form when seawater seeps down into the crust, becomes heated by hot rock, and rises back toward the ocean floor. The water that emerges from these vents is rich in minerals and chemical energy, and around these vents entire ecosystems thrive. Microbes, tube worms, and strange creatures live in complete darkness, powered not by sunlight, but by chemistry. If Titania has an ocean touching its rocky core, similar processes could occur there. Hydrothermal activity might create warm pockets of water filled with chemical energy, and in theory, those environments could potentially support simple forms of life. Titania as an ocean world candidate. Today, scientists classify certain moons as ocean world candidates. These are worlds that may contain subsurface oceans capable of supporting complex chemistry. Europa and Enceladus are the most famous examples, but Titania is increasingly being discussed as another possible member of this group. Although Titania is farther from the Sun and colder than Europa, its internal structure may still allow for pockets of liquid water. The key question is simple. Does the ocean still exist? Or did it freeze completely billions of years ago? Why we need a mission to Uranus right now? We simply do not have enough information to answer that question. Voyager 2 flew past Uranus in 1986, but it did not carry instruments designed to detect subsurface oceans. Modern spacecraft would be able to investigate Titania in much greater detail. Scientists could measure Titania's gravitational field, study its magnetic interactions with Uranus, and scan its surface for signs of cryovolcanism or internal activity. These observations could reveal whether liquid water still exists beneath Titania's icy shell. The Uranus orbiter concept. In recent years, scientists have proposed a mission called the Uranus Orbiter and Probe. This mission would travel to Uranus and spend years studying the planet and its moons. Titania would be one of its primary targets. The spacecraft could map Titania's entire surface at high resolution, search for geological activity, and possibly even detect evidence of internal oceans. For the first time, humanity could finally understand what lies beneath Titania's frozen surface. A hidden ocean in the darkness. If Titania truly contains a subsurface ocean, it would transform how we see this distant moon. Instead of a silent, frozen world, Titania would become a place where water still moves beneath the ice, where heat from deep within the moon slowly circulates through hidden seas, and where the chemistry necessary for life could potentially exist. All of it hidden beneath a frozen crust, drifting silently around Uranus. A mystery, waiting to be solved for now. Titania keeps its secrets. Its valleys stretch across the icy surface. Its cliffs rise silently into the black sky. And somewhere beneath that frozen shell, there may be water. An ocean trapped in darkness, waiting to be discovered. And until the day humanity returns to Uranus, Titania will remain one of the most mysterious ocean world candidates in the solar system. Far beyond the orbit of Saturn, where sunlight is faint and the solar system grows quiet, Uranus slowly travels through space. Unlike most planets, Uranus rotates on its side. Its axis is tilted by almost 98 degrees, making it appear as if the planet is rolling around the Sun rather than spinning upright. This strange orientation makes Uranus one of the most unusual planets in the solar system. And orbiting this tilted world is a remarkable collection of moons. Among them, one stands out above all the others: Titania, the largest moon of Uranus. The family of Uranus. Uranus has 27 known moons, each named after characters from the works of William Shakespeare and Alexander Pope. These names reflect a long tradition in astronomy where the moons of Uranus are connected to literature rather than mythology. The 5 largest moons are known as the major Uranian satellites: Miranda, Ariel Umbrio, Titania, Oberon. Each of these moons has its own unique story. Miranda is a shattered world of bizarre cliffs and chaotic terrain. Ariel is bright and geologically young with smooth plains and valleys. Umbriel is dark and ancient, scarred by countless impacts. Oberon, the second largest moon, lies farther away and appears heavily cratered. But Titania sits at the center of this family, as the largest and most massive moon in the Uranian system. Titania's place among the moons. Titania has a diameter of about 1,578 kilometers, making it slightly smaller than Earth's moon, but larger than many other moons in the solar system. It is larger than Pluto's moon Charon, and significantly larger than most moons orbiting the giant planets. Yet compared to the enormous moons of Jupiter and Saturn, Titania is still relatively modest in size. Ganymede, Jupiter's largest moon, is more than 3 times wider. Even Saturn's moon Titan is far larger. But Titania still dominates the Uranian system. It contains nearly half of the total mass of Uranus's 5 major moons combined. In many ways, Titania acts as the gravitational centerpiece of Uranus's moon system. Titania's orbit around Uranus. Titania orbits Uranus at a distance of about 436,000 kilometers. For comparison, Earth's moon orbits our planet at about 384,000 kilometers. This means Titania travels slightly farther from Uranus than our moon does from Earth. Completing one full orbit around Uranus takes about 8.7 Earth days. But Titania does something interesting during this orbit. Like many moons in the solar system, Titania is tidally locked. This means the same side of the moon always faces Uranus. The opposite side permanently faces outward into space. As a result, one hemisphere constantly looks toward the giant blue planet, while the other never sees it at all. The sky from Titania. Imagine standing on Titania's frozen surface. Above you, the sky would be incredibly dark. The sun would appear only as a bright star, far smaller than it appears from Earth. But dominating the sky would be Uranus. Uranus would appear enormous, many times larger than the moon appears in Earth's sky. Its pale blue atmosphere would glow softly against the blackness of space, and because Uranus rotates on its side, the view would change dramatically throughout Titania's orbit. At certain times, Uranus might appear tilted at strange angles across the sky. Its thin ring system would also be visible, faint bands of icy debris circling the planet. It would be a breathtaking sight, one unlike anything seen anywhere else in the solar system. The strange seasons of Uranus. Because Uranus is tilted so dramatically, the entire Uranian system experiences extreme seasons. Each pole of the planet points toward the sun for about 42 years at a time. This means that for decades, one hemisphere of Uranus and its moons remains in continuous sunlight. Then, for the next 42 years, it falls into darkness. Titania shares these unusual seasonal cycles. For long periods, parts of the moon experience constant sunlight. Then, they spend decades in darkness. This unusual lighting may slowly affect Titania's surface chemistry over time. Radiation from the sun interacts differently with ice, depending on how long it is exposed. Over millions of years, these seasonal cycles could contribute to subtle changes in Titania's appearance. The influence of Uranus's magnetosphere. Uranus also has a powerful magnetic field. But unlike Earth's magnetic field, Uranus's magnetosphere is highly unusual. It is tilted dramatically and offset from the planet's center. As Uranus rotates, this magnetic field sweeps through space in unpredictable ways. Titania moves through this shifting magnetosphere during its orbit. Charged particles trapped in Uranus's magnetic field constantly bombard the Moon's surface. These particles slowly alter Titania's ice through a process called radiolysis. Radiolysis breaks apart water molecules, producing oxygen and hydrogen. Over time, these reactions may create new chemical compounds on Titania's surface. Some of these compounds could include carbon dioxide ice and other exotic molecules. Comparing Titania to Oberon, among Uranus's moons, Titania is most often compared to Oberon, the second largest moon. Both moons have similar sizes and compositions. Both appear heavily cratered and ancient, and both orbit relatively far from Uranus. But there are some important differences. Titania shows clear evidence of tectonic fractures and large canyon systems. These features suggest Titania experienced significant internal expansion during its past. Oberon, on the other hand, appears more geologically quiet. Its surface shows fewer large tectonic features. This suggests Titania may have experienced more internal heating than Oberon, perhaps enough to briefly maintain a subsurface ocean. The mystery of Ariel and Umbriel. Two other Uranian moons offer an interesting contrast with Titania. Ariel appears surprisingly young and bright. Its surface contains relatively few large craters. Instead, Ariel shows smooth plains and long valleys, suggesting it was resurfaced more recently. Umbriel, however, looks very different. It is extremely dark and heavily cratered. Its surface appears ancient and largely unchanged for billions of years. Why these moons evolved so differently remains one of the biggest mysteries of the Uranian system. Titania lies somewhere between them, not as active as Ariel, but not as ancient and inactive as Umbriel. It may represent a middle stage in the geological evolution of Uranus's moons. The chaotic world of Miranda. Perhaps the most bizarre moon of Uranus is Miranda. Miranda is much smaller than Titania, only about 470 kilometers wide, yet its surface contains some of the strangest landscapes in the solar system. Gigantic cliffs rise more than 20 kilometers high. Chaotic regions appear, as if giant pieces of the moon were torn apart and reassembled. Some scientists believe Miranda may have been shattered by a massive impact long ago. The pieces later reassembled under gravity, creating its strange terrain. Compared to Miranda, Titania appears calm and orderly, but both moons remind us how unpredictable planetary evolution can be. Titania's role in the Uranian system. Because Titania is the largest moon of Uranus, it may play an important role in the system's long-term dynamics. Its gravity slightly influences the orbits of smaller moons nearby. Over millions of years, these gravitational interactions can shift orbital paths and create complex resonances between moons. Similar gravitational relationships exist in the systems of Jupiter and Saturn. Studying Titania's orbit and gravitational effects could help scientists understand how the Uranian moon system evolved over billions of years. A system, still poorly explored. Despite its fascinating moons, the Uranian system remains one of the least explored regions of the solar system. Only one spacecraft has ever visited Uranus. Voyager 2 passed by in 1986. During its brief flyby, the spacecraft collected invaluable data about the planet and its moons. But the encounter lasted only a few hours, and many mysteries remained unanswered. Half of Titania's surface was never imaged. Many moons were only briefly observed, and the internal structures of these worlds remain almost completely unknown. The next great destination. Today, many planetary scientists believe Uranus should be one of the next major destinations for exploration. A dedicated mission could reveal the secrets of Titania and its neighboring moons. Orbiters equipped with modern cameras and instruments could map their surfaces in detail. Radar systems could probe beneath the icy crust. Magnetic measurements could detect hidden oceans. And for the first time, we could truly understand the complex family of worlds orbiting Uranus. Titania's quiet orbit. For now, Titania continues its slow journey around Uranus. Every 8.7 days, it completes another orbit. The same face always turned toward the giant planet. The opposite side forever facing the silent darkness of space. Across its frozen surface lie valleys, cliffs, and ancient craters, each one telling a story about the distant past of the Uranian system. And somewhere beneath that frozen shell, there may still be secrets waiting to be discovered. Worlds hidden beneath ice, and stories written in the quiet language of distant moons. Far beyond the orbit of Saturn, in the cold darkness where sunlight is weak and distant, Uranus continues its slow journey around the Sun, and orbiting this pale blue planet is Titania, a silent moon of ice and rock. For billions of years, Titania has drifted through space almost completely unnoticed. Only once in human history has a spacecraft passed close enough to see its surface, and even then, we saw only part of the story. Half of Titania remains unexplored, half of its surface still hidden in mystery. But that may not remain true forever, because Titania could soon become one of the most important destinations in the outer solar system. The Voyager 2 encounter, the first and only spacecraft to visit Uranus, was Voyager 2. Launched by NASA in 1977, Voyager 2 traveled across the solar system, visiting the giant planets one by one. It passed Jupiter in 1979, Saturn in 1981, and finally reached Uranus in January of 1986. For a brief moment in time, Voyager 2 became humanity's only close observer of the Uranian system. As the spacecraft flew past the planet, it captured images of its moons. Among them was Titania. For the first time, scientists saw its valleys, cliffs, and impact craters in detail. But there was a limitation. Voyager 2 could only photograph the side of Titania facing the spacecraft during the flyby. This meant nearly half of the moon's surface was never imaged. Those unseen regions remain completely unknown even today. What we still don't know. Despite the data collected by Voyager 2, many questions about Titania remain unanswered. For example, does Titania still contain a subsurface ocean beneath its icy crust? How thick is its outer shell of ice? What exactly caused the giant canyon systems that cut across its surface? And what lies on the hidden hemisphere that Voyager never saw? These questions cannot be answered from Earth alone. Even our most powerful telescopes cannot resolve the fine details of Titania's surface. to truly understand this distant moon, a spacecraft must return. The growing interest in Uranus. In recent years, planetary scientists have begun advocating strongly for a mission to Uranus. For decades, most exploration efforts focused on Jupiter and Saturn. These planets hosted famous missions such as Galileo, Cassini, and Juno. But Uranus and Neptune remain largely unexplored. In fact, Uranus has been visited only once. Because of this, scientists consider Uranus one of the highest priority targets for future exploration. Studying Uranus and its moons could reveal important information about the formation of ice giant planets, a type of planet that appears to be extremely common throughout the galaxy. The Uranus Orbiter and Probe. One of the most promising mission concepts is called the Uranus Orbiter and Probe. This mission has been proposed as part of NASA's long-term planetary exploration plans. The spacecraft would launch from Earth and travel across the solar system for many years before reaching Uranus. Once it arrives, it would enter orbit around the planet. Unlike Voyager's quick flyby, an orbiter could spend years studying the Uranian system. During that time, it could perform multiple close flybys of Titania and the other moons. Each pass would reveal new details about their surfaces and internal structures. Mapping Titania in detail. One of the first goals of such a mission would be to map Titania's entire surface. High-resolution cameras could capture images far sharper than anything Voyager ever recorded. Scientists could study Titania's canyons, cliffs, and craters in extraordinary detail. They could determine the relative ages of different regions. They could identify areas shaped by tectonic activity. And, perhaps most importantly, they could finally see the hidden hemisphere of Titania. This unexplored side may contain entirely new geological features. It could reveal structures that change our understanding of the moon's history. Searching for an ocean. Another major objective would be searching for evidence of a subsurface ocean. Spacecraft instruments can detect subtle clues that hint at liquid water beneath the surface. For example, if Titania has an ocean, its internal structure may slightly alter the moon's gravitational field. Sensitive instruments could measure these tiny variations. Magnetic field detectors could also reveal how Titania interacts with Uranus's magnetosphere. On some icy moons, subsurface oceans produce distinctive magnetic signals. If similar signals were detected at Titania, it could confirm the presence of hidden liquid water. Radar. Beneath the IceFuture spacecraft may also carry radar instruments capable of probing beneath Titania's icy crust. Radar waves can penetrate ice and reflect back from deeper layers. By studying these reflections, scientists could estimate the thickness of Titania's crust. If a liquid ocean exists beneath the ice, radar might detect boundaries between solid and liquid layers. This technique has already been used successfully on other planetary bodies, including Mars and Jupiter's moon Europa. Applying it to Titania could reveal the moon's internal secrets for the first time. Understanding Titania's past. A dedicated mission would also help scientists understand how Titania evolved over billions of years. By studying the distribution of impact craters, researchers can estimate the ages of different regions. Younger surfaces contain fewer craters. Older surfaces accumulate more. Mapping these patterns across Titania would allow scientists to reconstruct the Moon's geological history. They could determine when its giant valleys formed, when its crust expanded, and whether internal activity continued longer than previously believed. Could Titania ever host life? The discovery of subsurface oceans on other moons has raised an exciting possibility. Could life exist in these hidden oceans? On Earth, life thrives in deep-sea environments completely isolated from sunlight. Instead of photosynthesis, these ecosystems rely on chemical energy. If Titania has an ocean in contact with a rocky core, similar chemical processes could occur there. Water interacting with rock could produce hydrogen and other molecules capable of fueling microbial life. Of course, Titania is extremely cold and distant. If life exists there, it would likely be simple: microscopic organisms living in dark ocean environments. But even the possibility is extraordinary, because it would mean life could exist far beyond the warm inner regions of the solar system. The challenge of distance. Reaching Titania will not be easy. Uranus lies nearly 3 billion kilometers from Earth. A spacecraft traveling there would require many years to arrive. Voyager 2 took almost 9 years to reach Uranus. Future missions may take a similar amount of time. Operating a spacecraft at such distances is also extremely challenging. Solar power becomes far weaker. Communication signals take hours to travel between Earth and the spacecraft. But despite these challenges, planetary scientists believe the rewards would be enormous, because Uranus represents an entire class of planets that we barely understand. Titania's place in the solar system. Titania may appear quiet today, a frozen moon drifting endlessly around a distant planet. But beneath its icy surface lies a history shaped by powerful forces: internal heat, expanding oceans, cracking crusts, and ancient impacts from wandering asteroids. It is a world that formed billions of years ago during the chaotic early days of the solar system, and it has been evolving ever since. Waiting in the darkness. For now, Titania continues its silent orbit around Uranus. Every 8.7 days, it circles the giant planet once more. Its frozen valleys remain untouched, its hidden hemisphere still unseen, and deep beneath its icy crust, there may still be secrets waiting: hidden oceans, ancient geological activity, or perhaps something even more surprising. One day, another spacecraft will return to Uranus, and when it does, Titania will finally reveal the mysteries it has guarded for billions of years. Until that day arrives, this distant moon waits quietly in the darkness, orbiting Uranus, far beyond the warmth of the sun, and far beyond the reach of human exploration, at least for now.